Hello everyone, and welcome back to another video. And in this video, I kind of just want to investigate a bit this integral right here. And what we'll arrive at, as you've seen in the thumbnail, is something, or a proof that's actually quite really cool. So what we're going to do is just kind of look at the integral from 0 to infinity of e to the minus x times the sine of x. And you might have seen this if you took like BC or something, or I guess Calc 2. Basically, we can just do this kind of rather straightforwardly with integration by parts. So let's start with that. What I'm going to do is just integrate this and differentiate that. So what this is just going to be is, well, not the integral, negative e to the minus x times the sine of x, evaluated from 0 to infinity, minus the integral of minus e to the minus x times the cos of x dx, and bounds, of course, and these minus signs will become pluses, and this term right here will simply just become 0 in the limit as x tends towards infinity, and sine 0 is just 0, so that's pretty simple right there. So then we're just left right here with this integral, which really isn't too bad in and of itself. We're just going to do integration by parts again, so we're just going to integrate this thing, integrate the e, differentiate the cosine, and let's see where that takes us. So what we have is a minus e to the minus x again, times the cos of x, evaluated from 0 to infinity, and then minus the integral from 0 to infinity of minus e to the minus x times minus sine of x dx. And what this leaves us with is just these two minus signs will just cancel. And you'll notice that this right here is just our original integral. I'll just call it I. And this term right here, evaluating it as x tends towards infinity, it's 0. But if you plug in 0 to this expression, you're going to get negative 1. But since it's an integral, we're going to subtract negative 1 and get 1. Hopefully that's pretty trivial at this point. But anyway, what we have is our integral is equal to 1 minus our integral, basically meaning that our integral here is just equal to 1/2. So yeah, that's pretty straightforward and nothing too crazy there. But the second approach I really want to look at in this video centers around if we do this integral but with, say, a series expansion for sine, right? So let's move it over here. Just kind of draw a line. So what we have here is the integral from 0 to infinity of e to the minus x times the sine of x dx. And, well, we know that, I'll write off to the side, we know that sine right here, I'll write a different color, sure. We know that sine of x, just by this series for sine of x is just the sum from n equals 0 to infinity of x to the 2n plus 1 over 2n plus 1 factorial times negative 1 to the n. Now, we can just sub this in, can't we? So what we're left with, or not left with, but what we gain is, why isn't it writing? Thank you, OneNote. All right, what we get is the integral from 0 to infinity of e to the minus x times the sum from n equals 0 to infinity of x to the 2n plus 1 times negative 1 to the n over 2n plus 1 factorial dx, of course. Now, one property of integrals and summations like this is that since there's really no x's in here, we can just reverse the bounds, as far as I understand. So doing that and also pulling out these terms right here, since they're constant relative to the integral, we can just pull them out. So what we're left with actually is just the sum from n equals 0 to infinity of negative 1 to the n divided by 2n plus 1 factorial times the integral from 0 to infinity of e to the minus x times x to the 2n plus 1 dx. And this is the point where you will probably notice that this right here is really just the gamma function, or sorry, not gamma function, it's the gamma function of x plus 1, which is just whatever this is right here, factorial, because we know that x factorial, or actually I really shouldn't use x. Well, no, we'll do like n factorial right here. It's just equal to the integral from 0 to infinity Oh, one note, please work. N factorial is just the integral from 0 to infinity of e to the minus x times x to the n dx. So this right here is really just, by this definition of the factorial, this right here is just 2n plus 1 factorial. And now this is kind of the moment where you see something fishy, if you will, is happening. That we have this right here in the denominator and this in the numerator. Meaning that when we expand this out, we get a 2n plus 1 factorial over 2n plus 1 factorial times negative 1 to the n. So something from 0 to infinity, of course. You'll notice that these will just cancel. And this right here just leaves us with the summation from n equals 0 to infinity of negative 1 to the n. The seemingly divergent series, well, if this really is equal to this integral right here, it does converge to I equals, or well, not I equals, but just to a half right here, as we just proved. And this is something that is really known in terms of like the eta function, right? So this right here is just the eta function at 0, which is defined to be a half, which might seem a bit convoluted at first, but let's actually take a look at what this series is kind of saying to maybe make some sense of it. So if we actually like write out the series, at least some of the terms at least, you end up with 1 minus 1 plus 1 minus 1. I'm not going to write it out anymore, you kind of get the point. So what we have right here is, well, if we sum this term, we get, well, so far this is just equal to like 0 if we sum these terms right here. But if we say add 1 minus 1 plus 1 minus 1 plus 1, we end up getting a 1. So which one is it? And the result we're left with is basically saying, well, it's actually neither, it's a half, which kind of like, this kind of makes sense, at least heuristically, because we're alternating from 0 to 1. But yes, anyway, this is just kind of a short video, but it's just a really cool video to prove that the sum from 0 to infinity of negative 1 to the n is actually just equal to 1/2. Abel series, I'm pretty sure it's called. Anyway, thank you for watching, and I'll see you on the next one.